And okay, now, hello everyone. Welcome to this week's Crunch seminar. Today we have two speakers. Our first speaker is Professor Adrian Lozano Duran. He's an associate professor in the Department of Aerospace Department at Caltech. He earned his PhD in aerospace engineering from the Technical University of Madrid in 2015. And from 2016 to 2020, he served as a postdoctoral research fellow at Stanford University in the Center for Turbulence Research. And from 2020 to 2025, he was an assistant professor at MIT as Aeroastro. His research focuses on computational fluid mechanics and the physics of turbulence, with particular emphasis on causal inference, modeling, and control using information theory. He is also interested in developing closure models for computational fluids through artificial intelligence. Adrian, thank you so much for your time today. And with this short introduction, you can start whenever you're ready.
Yeah, thanks a lot. I'm very happy to have the opportunity to present my work. So I'm going to be talking about information-theoretic approach to reduce order modeling in a broad sense. And then in particular, I'll show a few applications to fluid dynamics. I hope that you find it interesting. Before this, let me just acknowledge my group. So there are many people in my group that they have contributed with different components of this work somehow. So I just wanted to acknowledge them first. But if I have to highlight one person, I would like to acknowledge Yuan, because a lot of the work that I'm going to be showing is her work. So also a small overview of my group, what we do. So we have like three different thrusts. One is related to methods, is just related using new tools, many occasions information theory for causal inference, modeling and control. And I'm very interested in causal learning, in particular in complex systems. There is a component that is more about physics and models for turbulent flows, so how to introduce new techniques from artificial intelligence for computational fluid dynamics and applications to aerospace. So my background is aerospace, so I typically care about things that fly. And I have also a small component of experiments, usually PIV in wind tunnel to collect data, and this is related to also physics or using this for implementing the actual control strategies that we have and also for validation of the closure models that we develop. So today's talk probably is going to be kind of in between methods and the physics part and closure models. I'll highlight probably more methods because most of the time I'm going to be talking about methods, and that could be general for any models, not so much about fluid mechanics. But so the part of the methods, I'm just highlighting this kind of four of the branches, like causal analysis, like a flow decomposition analysis, and reduced order modeling and flow control. So this component here, I'm going to be talking about reduced order modeling. So let's start with the motivation. So essentially, we are looking at this system that you are all familiar with. I have an input, then I have something here is a model, and I have an output. This model could be anything. It could be an analytical model, it could be a simple linear regression, could be a very complicated transformer model. But what I'm interested in is to understand what are the limits of what a model can predict. And let me motivate this with this example. So imagine I give you the driving licenses of everybody in the planet. And I tell you that I want to predict the weather. So like construct a model that you can predict the weather using as input the driving license of everyone. Well, but you will tell me probably, well, this is not possible. But then I will tell you why not. This is 400 terabytes. This is a lot of data. So I'm giving you a lot of data. Why you cannot predict the weather? You have a lot of data. But you see in an intuitive way that this is not going to work. But in a way, the question is, why not? I imagine I tell you, actually, let's use this. Let's use the state-of-the-art transformer or any AI tool that you want. So can you make it happen? So again, you will tell me, no, I cannot make this happen. I mean, this is not going to work. So this is the question that motivates actually what I'm going to talk about. So why can we use all the driving licenses on the planet to forecast the weather? And the answer you probably know is kind of obvious, is that it's not possible because all this information, even if it's a lot of terabytes, they do not have any content about the weather. So there is nothing about the weather in all that data set. Um, so this example is just to motivate the question. And I know that this is kind of obvious, but think of other cases might not be so obvious. Imagine now this more realistic case. Imagine this case. I have a sensor array located in different locations, and they can measure some pressure and temperature. And then I ask you, can you forecast the weather within to 20% error using this array of 25 sensors? Then it's not so clear if the answer is yes or no. I mean, it's obviously that you cannot predict with 0% error, but maybe with 20%, maybe it is possible actually. So what is, this question is exactly the same as before in a way. So I'm just asking you, given this input data, what can you predict? So this is the goal of this talk, is to investigate this like a fundamental limits of predictability and from an information theoretic perspective. And this would be independent of the modeling approach. And you saw that in my previous example. Somehow the answer has to be related to information. That's the input has information about the output. And as you can see, it doesn't matter what is the model that you put in between. And that's why I also use this transformer example. So there is something even more fundamental about what you can predict. So here I'm talking about information. And then the next thing to clarify is that what do I mean by information? So before that, I'm going to highlight 3 papers. There is no one single paper that contains what I'm going to be showing here today, but if somehow all the theory is spread around these 3 papers, one is information theoretic formulation of dynamical systems. Another one is related to extreme event forecasting in Caltech systems. And then the last one probably is the most important one, dimensionless learning based on information. So if you want to see many of the examples that I'm going to be showing here, or if you want to learn more about the math behind, so you can take a look at these papers. So now let's go back at what do I mean by information. So information is defined here within the framework of information theory that was essentially established by Shannon. And it's a concept about variables that they look random. So we have a random variable and it has some probability distribution. So my random variable here is pi, and p is the probability distribution. So in an intuitive way, we define the information of one event as the log of the probability of that event. That at the beginning might look not so obvious why, but I typically give this example that is, imagine that this is my dynamical system. My dynamical system is to flip a coin n times. So I flip a coin n times, that's my dynamical system. So then I get a sequence of heads, heads, tails, tails, whatever I get. So what would be, according to this definition, the information? Well, it will just take the log of the probability of that event happening, and that's n, and n bits. So you can see that flipping a coin n times, because the coin is binary, and I did it n times, it gives me n bits. So then you can think of a system that doesn't need to be discrete, the variable could be continuous, but the idea is the same. I mean, when we are talking about information, we are talking about how many megabytes we have in a variable. And that was the information of one event, but typically we work with the Shannon information, that is the average amount of information. So this is this h, and using capital pi is just the random variable, and this is the expectation of all the one event information that you can get. And again, this could be for a discrete or random variable. So we just make the average over all the possibilities. And the other quantity that matters here in this talk is the conditional Shannon information. So this is the information in a variable pi1, discounting the information in another variable pi2. And we denote this with this h of pi1 condition to pi2. And you can also understand this in an intuitive way, is that imagine that I measure pi2. So what is the remaining information in pi1? So that's what this means. And this is going to be the key quantity, actually. So we don't need barely anything else to define the framework. Okay, so this is the outline. This is what I'm going to talk. I'm going to talk about 3 things. The first one is I'll talk about how this error in any model can be thought of as a lack of information. And I've introduced this information theoretic limit to modeling. And derived from that, there are some interesting applications. I pick some of them. Is like generalizing the Buckingham Pi theorem, defining a model efficiency, and a few more. And the third point is applying this framework in a more particular setup that is large eddy simulation, and discuss the origin of closure problems. And maybe for those of you who work on fluid mechanics, and in particular in LES, this might be familiar. So let's talk about formalizing this concept of the error as lack of information. So this is essentially a bit of notation or just to set up the problem. So typically, anytime that you construct a model, you can think of the model in this way. You have some variables, Q1, Q2, until Qn. And then you want to predict another variable that is Q naught. So the naught is essentially output. So you write a relationship like this, and this F is your model. And again, could be anything from analytical to a CNN. And then you will have some error. And this is fair. So this is something that you can work with. But typically, at least because in physics, we like to work with dimensionless variables. I'm going to immediately rewrite this in this way. I'm going to have a model in dimensionless form. And to do that, you might be familiar with the Buckingham pi theorem. It will tell you that for any dimensional model, you can derive a dimensionless one. And now I'm using this pi. So these pi variables, they don't have units. And it's just rewriting the first model. Now I have a different f of the model. This is dimensionless, and it will depend on m inputs plus on error. The error is still there. And this already has an advantage that you can reduce a bit the number of inputs by NU, and the U is the fundamental units in your problem. There are 7 fundamental units, and those are typically the length, the time, the mass, electric charge, and so on. Okay, so now this is what I'm looking at in a very generic way. And I want to understand this error here, regardless of this F connecting the input and the output. So now is when the information theory comes into play. I'm going to use this schematically to represent the information content of different variables. So this H, if you remember again, this is the Shannon information, and I have n variables. So this is the information contained in all my input. Then I have the information contained in all my output. And I'm going to use this orange, and this is the pi output. So already in this schematic, I'm trying to represent this idea, that it's the intuition that we have before. I have information in my input that actually is independent of the information in my output. It's not useful, it's unrelated. Then there is an overlap. This is the overlap here, is actually called mutual information. So because it's the information shared between my input and my output. And then there is the rest of the output. So the rest of the output is information that is in my output, but is not in my input. And this is the problem, in a way, reduce all the modeling. This magenta region, you can work out what it is. It is the information in the output once that you account for all the information you have in your input. So conceptually, what we can think of is that the accuracy of any model, it has to be somehow fundamentally limited by this amount of information that the output has, but is not contained in the input. In a way, you can not predict anything that is not already contained in your input. Everything has to be extracted from your input. And this is conceptual, but you can formalize this. You can actually get a connection. And this is the connection. Probably the only equation probably I'll be showing here is this was done in Yuan recently with my student Yuan and myself. And what we have here is this a bound in the model error. So let me walk you through what this means. So what we have on the left, this is the error in the model. So I have the quantity pi naught that this is the truth. And I have the quantity predicted. And I'm deciding to measure this error in some norm P that I can choose. So this has to be bounded by this quantity here. And in this quantity here, it depends on this exponential of this entropy. And this is exactly the entropy I was referring to before. This is the information in the output not contained in the input. A small difference with what I was showing before is that there is this alpha. So I introduced the Shannon information. There is a generalized version of that. It's called the range information of order alpha. And you can show that that is more useful in this case. But conceptually, it means the same. It's the amount of information in the output that is not contained in the input. And now the input is bold, so it's a vector of all your input variables. And then there is this, that this is a constant. So it's not related to information. This is just a function of two things. What is the alpha of your entropy? And then what is the p norm that you choose? And this is true for any alpha and for any p norm. So will always be satisfied, this condition. So now you can see that this is the interesting equation because we found a link between how small can be your error and a quantity that depends on this information. So a few also interesting observations of this. There is, when I showing you this equation, there is no model here. So this is for any model. I didn't specify F. The F of the model doesn't show up here. So it could be an analytical model, a linear regression, it could be a feed-forward neural network, or it could be a diffusion model. It doesn't matter. So this is a lower bound of on predictability. Another interesting detail of this equation is it's sensitive to the norm. So if I change the norm, then it will change the bound. So that you can think of these in, for example, extreme events. Sometimes some events are, depending on the magnitude, they might be less difficult or more challenging to predict. And this bound will adapt and account for that. Another thing that is interesting of this bound is that this is a property of the conditional entropy, is that invariant under bijective transformation. So I can transform my input and output variables using a bijective transformation, and this bound will remain the same, so it doesn't change. So this, again, is not a property of the particular way you write the variables. It's more fundamental. It's a property of the information in your variables. And bijective transformations, they don't destroy information. So that's why you can just apply them and you will get exactly this relationship. Okay.
Adrian, I have a question. In this part, like, what were like the assumptions that you made? Because this looks somehow similar to this. I was asymptotic equipartition property, something along those lines. Like, we had like, are you are you assuming that we have some kind of typical sequences, typical sets that we're going to identify in this kind of like in the place in the pink area of the mutual of the information that you mentioned?
So I would say that probably assumptions are not very stringent. The only assumption here is that you can define a probability distribution of your variables. So as long as that exists, so as long as you can define the joint probability between your input and output, then this bound applies. Yeah.
Okay. Okay. Thank you.
So another way that is also interesting of formulating this, I like to think about this analogy. I don't know if you are familiar with thermodynamics. So there is something that is the Carnot cycle of an engine. So the Carnot cycle of an engine is there is a particular, you have some heat sources. One is hot and the other is cold. And then you have a gas to work with, and then you start expanding the gas and compressing the gas. And then you can extract work. And then what Carnot show is that there is a cycle that is optimal. And that means that there is a maximum amount of work you can extract from some particular setup. And regardless of the technology of the engine. So if someone comes to you and says like, oh, I have these conditions, this heat source, and I'm extracting this work. And then and it was like, I'm extracting this amount of work because I have this new technology, you could already say, okay, that's not possible because it's a fundamental law of physics that you cannot. So I like to think of this as an analogy of the same, but of models. So you have some amount of information in your input about your output. And there is a fundamental limit of how much accuracy your model can extract. So if someone comes to me and have a model that is 99% accuracy, I could actually, looking at this, say, okay, that's not possible. Given this input and this output, that's not going to happen. Again, this doesn't tell me what the model is, but this tells me what is the best possible model, because the best possible model is the one that matches this bound. Okay. Sometimes you can think of problems that are classification. So this bound could be recast in a different form, that instead of talking about error, we can talk about probability of error. So you can think of a classification problem. For example, there is extreme event, yes or no. So in that case, it's similar. It's like a probability of error as lack of information. So we have a probability of error, like a probability of making the right answer or not. Again, there is a function here, h alpha of -1 is here. It's not so important, but what matters again is this quantity shows up again. It's just the bound, the form of the bound changes. So this is the information in the output, not contained in the input. So sometimes you can use the previous bound that is defined as literally the error, like in some LP norm, or sometimes you can just use the probabilistic version, is the probability of some error. And these are some examples where we are interested in our group related to, well, intense oscillations of loads or the bumpy flights on gas or some vortex-induced vibrations. So in typical, you have some signals that are highly intermittent, and then that's essentially what you just care about, not so much the value, but if the value goes above a threshold. Um, so with that, that's essentially the formulation of the problem, and that's the connection between error and information. But from there, we can derive some applications that can help us to inform models and construct models and also learn about models. And I'm gonna go over a few of them. There are more than this. This schematic is literally taken from this Adrian Lozano Duran 2025. I'm gonna discuss like 4 applications that are derived from the theorem. Let me talk about the first one, dimensionless learning. So I'm just bringing back again this bound. We can think of this as a way of picking the best dimensionless inputs. And this is what we call this information-theoretic Buckingham Pi theorem, so IT-Pi. So I can ask this question. There is this dimensionless output and this dimensionless input. And there are an infinite number of ways of generating dimensionless variables. And the original Buckingham Pi theorem, it will just give you a recipe to obtain any of those. It will give you infinite of those and you just pick one. But what you can do with this bound is to pick the best one. How? Well, it's just very simple. I want this bound here that I'm calling epsilon LB, so lower bound. I want the error lower bound to be as low as possible. So these dimensionless input that yield the most predictive dimensionless output are the ones that solve this problem. So I'm minimizing with respect to the input and the output. And this asterisk is the best solution. So the first thing that we'll get from here, we'll get what from all the infinite possible dimensionless input and outputs, it will tell us what are the best. The second thing that we get from here is also very useful, is this lower bound itself for the model error. And this is this epsilon asterisk lower bound. That is the error that you get for that particular set of variables. And again, what I highlight here is that this bound is independent of the model. So I can know this a priori. And then this is going to be very useful later to define an efficiency of the model. And I'll mention that one of the applications here.
Yeah, one question like here. But in this case, how do you, because one of the problems that I have seen, like when it's related with the information theory, for example, in this information bottleneck theory and things like that, is that sometimes it's a bit tricky to get a good estimate, for example, of the entropy. How are you computing the entropy?
That's
It's
true. So probably that would be the main challenge of the approach, that you are not going to get this lower bound. You are going to get this lower bound plus an error that you can estimate. And that error might be so large that this bound is not relevant or is insignificant, or it might be low enough so you actually are confident of what that bound is. And that will depend on your problem and the amount of data that you have of your problem. If you apply this like in a data-driven approach, I mean, you could do this analytically. If you know the probability distributions of your system, this will just be no error at all. Obviously, that's not realistic. In most cases, you apply a data-driven approach and you collect data. And in that is very important, obviously, to not only compute this bound, but also some error bars for that. And that will tell you whether this is significant or not. Now, how you estimate the entropy, then also depends on the problem that you have, the dimensionality of the problem that you have, and also the amount of data that you have. But there are different tools that you need to choose correctly depending on that. I'm not talking about that here, but in general, people that essentially all their lives is to estimate entropies. So there are tools there.
Yeah, but in your experience, in the example that you're showing, like what was the general method that you used to estimate the entropy?
So in this particular case, we just use like a estimator typically. So we can use, we do it in a different way. So we can use a kernel estimator. We can use the Krakow estimator, that's what the estimator is typically used. And we can use a neural mutual information estimator. And the idea, for those that are upper and lower bounds, and the idea is that your answer is independent or is within some margin for all the different estimators that you have. If you have very low dimensionality and a lot of data, you can even just apply the definition itself and do a binning method. And sometimes it could be done. So in a way, we always try to make sure that that the answer that we get is independent of the method we apply. So that should be the goal always.
Oh,
And if it's
okay.
not, then it's not reliable, the answer.
Okay. Thank you. Yeah, because in most cases, what I have seen when they have data, they do this, as you said, like the binning method. But then there was like a lot of ambiguity because it depends, like the way that you choose your beans will give you a slightly different answers. And
So if I'm honest with you, this particular lower bound might be sensitive, this numerical value, but the one that minimizes this bound, like these variables, usually are much less sensitive to that. So yeah, but it depends on the problem. Yeah.
okay,
So the next thing is related to just right away like that, like a predictability ranking. I can just rank my inputs in order, depending on as I have a different input, what is the error lower bound that they give me, and I can short them from the worst input to the best input. Actually, I can also know what is the optimal number of inputs that I need. So there's a point in which I shouldn't add more inputs because they are not reducing the lower bound. So I need L inputs, and that's what I'm showing here. And this can be done, the ranking is not only like a variable wise, it could be done by pairs, it could be done by triples. So I can also organize all the different combinations of two variables, what would be the best one, and or for three variables or four variables. And depending on how complex I want my model to be, then this will help me to choose, okay, if I only want my model to depend on two variables, these are the two best variables. Uh, this is also referred to more in the machine learning jargon, like this is a feature selection approach. But what I like of this approach is like directly linked to the error of the model. Um, Another that is more related to physics is to identify physical regimes. So what is a physical regime? So this is a operating condition of your system in which that is governed by a particular set of dimensionless variables. So one example could be in fluid mechanics. You can have the incompressible regime, and that regime depends only on Reynolds number, one variable. Or you could have compressible regime that depends on two variables, Reynolds number and Mach number. So you can actually have a map, like imagine a problem in which I have only two inputs. I could create a map that will tell me if that one input is important or not, and divide the flow in my space of inputs in regimes. And that's done just computing a ratio of this entropy. So how much this variable is computing to reducing the error compared to considering all the variables. Um, and the last part is the model efficiency. That is also a nice feature here. So if you think about, I have my model, could be again anything, like one predict my output given my input. My model is I have to define a structural form, and then I will just fit or train my model, learn the model, and that will give me some error. So ideally, I could compute this ratio. I compute the ratio of the best possible error that I have, epsilon lower bound, compared to the error that I'm actually getting from my model. And this has to be bounding between 0 and 1. So 1 would be 100% efficiency. It means that I found the best possible model, and then I'm done. I don't need to keep looking. Or it could be lower than that, could be, I don't know, 0.5. So it means that there is a lot of margin for improvement. And I should probably keep looking, or I'm not using the correct structure of the model, or I'm not training in the correct way. So this is another feature that is useful. And there are more things that you can do. I will refer back to the work of with Yuan. So you can also use this to detect self-similar variables. there is also a nice theorem for dynamical systems called embedding theorem that will tell you how many time lags you need to reconstruct a manifold. So it could be also recast in these terms. We can also talk about synergy and redundancy between variables. Some variables, they are synergistic. So when you put them together, you can predict much more than adding them individually. And redundant is like some variable contains the same information as other ones. So actually you can just drop one of them because it doesn't matter. So all this in a way goes back to using that connection between error and information and to detect these kind of features. But for sake of the time of the presentation, I decided not to talk about all that. And instead, I wanted to show you a real application that we did in our group. So this application is now related to fluid dynamics. So what you see here, this is a hemisphere that is moving very fast. And what you see in the color here is the temperature. This is a hypersonic flow. So even if you don't see here, there is some roughness over the surface. This is a 3D simulation, although I'm just plotting a 2D cut. And blue is cold, and then red is hot. So you can see how the air gets hot. This goes closer to this hemisphere. And then there is this bow region. This is a shock wave that is formed. So the idea was that we wanted to have a closure model at the wall to predict the heat flux and the forces at the wall in this system. And the way this is formulated, imagine that I look in a small region here. This would be my grid. So this is now computational fluid dynamics. I grid my problem, and the grid would be some structure. So these would be these blue cells. And now I want to extract some information of the flow around. And this is the wall. And I want to predict the fluxes at the wall. So the way we do that is there might be some roughness that is not resolved by our grid because it's very fine. So there is some coarsening in the simulation. At the wall, we can provide some roughness parameters. So these characterize statistically the roughness, so the typical height, the typical slope. And then far from the wall, we can collect some information about the flow, like the density, the velocities, the temperature, some properties like conductivity of the gas. And we pass all that information into our model. In this case, it's a simple model, just feed-forward neural network. And then we predict at the wall the fluxes. And these fluxes, again, are the heat flux and also the washer stress. And we have a large collection of data to do that. The data doesn't contain this case because this case is a case that we cannot compute with high fidelity, but we have simpler cases of the order of 400 cases in which we have different roughness and this is a turbulent flow over a wall and the flow is compressible, so different Mach numbers. And we want to learn from all that data set, we want to learn these relationships. So this is the setup. And the first step is, before I even try to train any neural network to do that, the first question I want to answer is, what is the input and what is the output in dimensionless form? Again, because in a physical problem, it's always more convenient if you formulate it in dimensionless form. So for that, this is the statement of the problem in a way. The tau wall is the stress at the wall, the Q wall is the heat flux, and it depends on all these parameters that they have dimensions. But what we did is to apply our ITPy here, and the conclusion that we get from here is first that we will get exactly what are these dimensionless numbers for the output and for the input that we need. And we also get that we need only two of them to already get a very high efficiency. So how does this look? So this is how it looks. So the blue boxes is what we did like a priori before training the model. So we have some variables here that, as you see, they look like a bit like a monster. So these are a way of combining these variables. I even simplify this a bit further, rewriting these variables into another dimensionless numbers and then as these ones. So this is the vector of two inputs for the stress at the wall and the vector of two inputs for the heat flux. And the other conclusion that we got from applying the ITPy is that there is a lower bound error of 4%. So that's the minimum error we will get. And now these are the dimensionless output. So now that we know this, then we train our feed-forward neural network. And two nice observations here is the first one is that we can adjust in a way the complexity of the model, meaning the learnable. So how many free parameters we have. What we do is to increase the complexity such until we start from very simple network and we start increasing the complexity until we achieve 100% efficiency that I can compute, because if you remember, is the performance of my model compared to the best optimal performance theoretically that I could get. So when we get something like 98%, something like, then we know that we don't need to keep increasing complexity of the model. So that's something in which this is useful. And another observation here is that well, first, these inputs are highly non-trivial. I don't think like a person just thinking will come up with this particular way of arranging these variables. So it really requires applying this optimization with ITPy. And we checked actually that if we change any of these variables, then this model efficiency, sorry, this lower bound will go up, meaning the error will go up. So in a way, maybe these variables are not the best for physical interpretability, might be very difficult to interpret, but because this is reduced order modeling, we care mostly about predictability, so they are very good for predictability. And the other point that I'm highlighting here is that imagine I don't know anything about this information theoretic approach. The traditional way will be I apply the Buckingham-Pi theorem, and the Buckingham-Pi theorem will tell me that I need 7 inputs. Instead, well, I mean, you won't get that you need only 2. Here we know we need only 2 to achieve this very low error, but the equivalent in Buckingham-Pi will tell you you need 7. So 7 input and 2 is from the point of view of the amount of data that you need is massive. So this can be done without overfitting with a few thousand samples. We have even more than that. But if you move to a 7 input dimensional space, these simulations where we get this data from are very expensive, and then suddenly your input space is almost empty, and you are overfitting, and it's actually the model that you get is actually worse. And it's worse not only because you have more inputs and the model is more lost, is because the variables are not aligned in a way like they are here, such that they predict the output the best. So I'm now showing a deployment of this model. So these are actually implemented in a solver. This is some details of this case is a Mach 6 high Reynolds number, and again, temperature in Kelvin here. And we were comparing the heat flux along the arc of the hemisphere. And we just wanted to see that our approach is, this is world model LES, using this model for the fluxes at the wall, that we were able to predict the heat flux. And we also switch off the model, not using it at all. Those are the blue dots to see that the model is actually doing something is different. So these are actual deployment, or in a way, and so an application of how we can use this in a useful way, or how we have used this in our group. So the last part is still related to this lower bound, but I wanted to make it a bit more particular to large Eddy simulation, and this connect with this idea of the closure problem, or where does it come from? And so for those of you that are not very familiar with large Eddy simulation, essentially this previous example that I was showing of this hemisphere flying very fast, it was done with large Eddy simulation. So large Eddy simulation is a reduced order model of Navier-Stokes. So when we solve Navier-Stokes with the highest fidelity, we solve all the scales in space and time. That's what we call DNS, direct numerical simulation. But typically for realistic cases, the number of degrees of freedom, that is n, could be very large, like 10 to the 9 or 10 to the 30, even if the case is very complex. So that's not acceptable. And the reason for this high number of degrees of freedom is because you have motions in the air that are of very different size. And the smallest ones are very small. So you need to have a very fine grid to resolve them. So the idea of LES is that you have a grid like this that is coarser. So I'm just trying to denote here these eddies of different sizes. Some of them by this grid are resolved, and others are so small that cannot be resolved by the grid. So they are much smaller than the grid, even sometimes like 1,000 times smaller than my grid size. But by this, I can reduce the degrees of freedom now because my grid is much coarser. So maybe I can have 10 to the 4, 10 to the 9. And this is, I move something that was barely feasible to something that is okay. I can use a supercomputer and at least solve the problem and get an answer. But there is a price to pay, obviously, because now many of these degrees of freedom are dropped. So what is the consequence of that? So what we typically do is to modify the equations. So this is just conservation of momentum. without this last term, it would be DNS, but because my grid cannot resolve all the scales, we need to add an extra term that is the Sagrid scale model. It's a correction for the fact that we cannot resolve these small eddies. So I'm not going to talk yet about any particular model here. And actually, I'm going to try to step back now and try more conceptual about this problem. I want to talk about, again, what happens when you lose information and what is the consequence of that. So now let's reformulate this problem in a more generic way. And it's similar to what I had before, but I'm thinking now from the point of view not only of modeling, but reduce order modeling. So I'm going to think of first the full system and then what happens when I reduce it. So in that case, I have my state vector, could be velocity, pressure at all my grid points from 1 to n. And this n is the one that is massive, is very large. And I have an equation that maybe is known in some cases. So formally, I know the equation. It's like it's unsolvable. And I can write that equation like this. I want to predict my quantity, my state vector in the future, some t arbitrary. And there is a function that will give me that. But again, that function is very expensive to evaluate. So what we do following this example of LES, I divide my state into two components. One is I call resolve, is the Q tilde, and the other one I call subgrid, is wherever I'm going to drop. So these are the degrees of freedom of my model. So my model can work with this Q tilde, and this is information I can access. And the Q prime is the degrees of freedom that are lost. So this information my model doesn't have. So I can now write the model, exact model, still for the Q tilde. The Q tilde is still a function of both the resolve and the subgrid. But this is not useful again because I'm considering the full system. This Q prime is massive, so I need to drop it. So now this is the actual model. My model is, I want to predict this in the future, the Q tilde, but I only want to use information that is resolved, and the subgrid information is lost. So if we go back to the diagram, if you remember, I'm going to rewrite it, but now thinking of the subgrid scale component. So I have this information in Q tilde, and this is represented by Q. And then I have the subgrid that I have here. So as before, there is some part information in where I want to predict the resolve component, that there is an overlap between the resolve component and the prime component that is subgrid. But there is also information in the Q prime component that cannot be recovered from the resolve component. And the last ingredient that we need here in this schematic is what I want to predict. So in the future, I want to predict this quantity. I'm calling this Q tilde plus. So it's like from Q tilde, I want to move to the future and predict Q tilde plus. And let's say that that information is represented by the purple. So in this schematic, you can, again, work out the different regions. And the problem is, again, this. Why? Well, because this is information that is in my variable in the future, but is contained in these degrees of freedom that I dropped. So that information was lost. And then you can apply or rewrite the previous bound, actually, just to show up this Q prime if you want to. But the bound is essentially the same. So what are the consequences of this from the point of view of a reduced order model that is dropping degrees of freedom? So the first implication is, in most cases, if you have a chaotic system, non-linear, where everything is coupled, exact future predictions are impossible. There's just no way. You cannot construct a model that will exactly predict the future because of this magenta region. And how bad that is going to be is related to how big is this magenta region. But in general, at least in the problems I care about in fluid mechanics, the conclusion is that it's not possible. So that's not going to work. And the other part that is interesting from the point of view of LES is that LES, many people think about LES as you take your equations and you filter. And the filter is what gets rid of this grid scale component. And I mean, that's okay. But I never mentioned any filter here. I think that this gives maybe a different perspective in terms of information. To me here, the problem is not filtering. The problem is losing information. So sometimes your filter might destroy information, but sometimes might not. So actually, if you derive your equations for LES and you apply a filter that is reversible, there is no closure problem at all. So information is conserved. That's why it's a bit, in my opinion, misleading to use filter DNS data to derive closure models, because the filtering act is not the problem. So it might be that your model is not so meaningful. If you apply a non-reversible filter, those they destroy information. And now you have a closure problem. But again, the problem didn't come from the filter. The problem came from destroying information. And another way of destroying information is if you coarsen your grid. So if you do some coarse graining, meaning you decrease the number of grid points or you decrease the number of Fourier modes, then you destroy information again, and there is a closure problem. So to me, this kind of illustrates that the fact that filtering your equations, it doesn't necessarily actually introduce a closure problem. It's more the fact that you destroy information. And definitely when you coarsen your grid, that will happen. And this is also important when you are going to train, for example, some machine learning models that typically people tend to use filter high fidelity data. So again, that might be not very well performing later a posteriori. And I wanted to illustrate, and that's the last thing I want to talk about today, illustrate this point, a very silly example that I did some time ago, just to show that the closure problem actually is not related to the filtering. So this is the filtering viewpoint versus the information viewpoint of LES. I took this simulation. So this is a box with a flow. It's incompressible, and I'm plotting here the velocity. And I perform a direct numerical simulation. So here I have, this is the number of grid points, 512 cube. I solve this equation, and this equation is Navier-Stokes. So I'm resolving all the degrees of freedom. I integrate this in time, and this is my solution. After some, these are called the integral time scale, so 10 integral time scale. And this is what the flow looks. Now I can apply a filter to this. So now I remove the small scales, but this is a differential filter. So differential filter is a filter that doesn't destroy information, it's reversible. So now I can integrate my equations. These are filter LES equations. I know exactly what my grid scale model should be analytically because I can invert my filter. And it looks like this is my correcting term in the equations. So now there's a correcting term. I can apply this and I can integrate this in time, and I can get the solution at the same time as the previous one after 10 units for this LES that has been obtained by filtering the equations and the initial condition. And then I can apply the differential filter to this equation, and I can compute the error. And then the error is actually like 0.1%. I mean, nothing happened. I mean, I was able to resolve these large eddies with almost 100% accuracy. There was absolutely no problem with that. And the reason is because information was conserved. So the filtering didn't introduce any closure. And the key here is this number of points. And by keeping the number of points and using a reversible filter, then comparing these two solutions will me a small error. There is always a small error because of truncation in the numerical scheme. And now imagine that I change one thing. I just applied the same one, but I put this in red. Now I coarsen my grid. Now error is 100% actually. I mean, it has nothing to do with the solutions because I lose information. So now future is, I cannot predict point-wise what is going to happen with all these. This will be my Q tilde in my notation before. I cannot predict that. Okay. So this is an example to illustrate one of these, how thinking about in terms of information in this application of LES. So with that, I'm summarizing conclusions here a bit. So essentially, I hope that you found this interesting. I tried to think of the problem of creating models from the point of view of information. And the first step was to discuss this connection. And what is nice about this connection is that it's independent of the model and is sensitive to the norm. And then you can derive many applications from here. And I show you today this information-theoretic Buckingham Pi or predictability ranking or the regime detection, model efficiency, and how you can use that in practice in some cases to apply a model. And then I apply the framework. I reframe it a bit from the point of view of large eddy simulation to try to argue that this closure problem doesn't come from filtering, that is the typical approach in the field. It comes more from the losing information. So when you construct your model, in a way, you need to take that into account, that maybe the filtering, the high fidelity data is not the way to go. And I will refer now to these papers that I mentioned at the beginning. There are many details there. There are many interesting examples and toy problems to illustrate the use of this bound. And then I think that's it. I kept it. I think that maybe because I started late, I'd be happy to take a few more minutes for some questions.
Yeah, thank you so much, Adrian. That was a really nice talk. Do we have any questions from the audience?
Hi, Adrian, this is Raj. I just had a question on 70, just slide before this one. Yeah, here. Can you explain a little bit more like how do you go from the initial condition to that prediction? So I was just not sure like what are the inputs and what are
Yeah,
the
let me
features you
go,
use?
let me go over this again.
Yeah.
Maybe it was my bad that I didn't explain it in a lot of detail. So let me start from here again.
Yes, yeah.
This is, there is nothing fancy here. I have my simulation. This is initial condition that is already a nice flow field. And I integrate this in time solving Navier-Stokes. And after 10 time units, this is the velocity that you get.
Exactly.
So now what I want to do is I want to do the same, but only for the large scales, because that's what LES would do is to neglect the small eddies and only integrate in time the large scales. So to do that, I prepare this new initial condition. I take the original one and I filter it. So now, as you can see, the small details are lost. And
Yes.
I have the large detail. Okay. So according to this concept now, if I apply the filter equations to this, then I have a closure problem because I have a correction term. And what I'm trying to argue here is because this filter and this particular filter that I'm applying is reversible, is the differential filter. On the top, I have the LES equation. It looks like the one on the DNS, but plus this last correction term.
Exactly.
And then I have the analytical formula for the Sagrit scale model. And this analytical formula you can always get as long as your filter is reversible. This is one particular case, but any reversible filter, you can write down this equation. So I can take this, and this is what I use as a Sagrit scale model. So up to this point, in a way, everything is exact. But I'm integrating an equation that looks like this. It looks like there are no small scales. And I integrate this after 10 time units, the same. So if this is true of kind of what I was mentioned before, because no, I never lost any information in this approach, the largest scales of this case, LES, should actually match the largest scales of this DNS. And that's what I was trying to show here. How do I show that? Well, you see qualitatively here, they look very similar. But the way to show that is like, okay, let me take the previous DNS, let's get rid of the small scales. And I apply the same filter as I'm using for my LES, and I get this. And then I compare these two. And the fact that these two, they match almost exactly, it means that I have an equation that was able to integrate my large eddies exactly. So there was no closure at any point problem. So the problem, no closure in the sense that I recovered the same solution. But and what I argue is like this is because this approach, this LES is a very particular LES. It's an LES that conserves information.
Okay.
To conserve information, I needed two conditions: to apply this reversible filter and to keep the same number of points. I couldn't coarsen my grid. And to show that if I coarsen my grid, every time you coarsen your grid, you will lose information for sure. So I just repeat this, but I reduce the number of points to this, like 1/4.
Okay.
And now the error is 100%. Why? Because the fact of doing this, I'm losing information. And every time I lose information, as I showed before, if I go here to my consequences, it was the first line. The exact future predictions are impossible. And that could happen because of non-reversible filters or because of coarse graining. So this is an example of coarse graining. My filter is reversible, but because I do some coarse graining here, now my error in the prediction is 100%. Like this, and you can already see this here. I mean, they have nothing to do, essentially.
Yes, makes sense. Yeah. Just one question that in the top row, the last figure where you applied differential filter on at solution at T. So this different output after differential filter should satisfy this LES equation, right?
Yes, and it does. Yeah.
Okay. And one question on Buckingham Pi, that is just to non-dimensionalize the input, right? That
is both the input and the output. So You can choose in a way wherever you want, but if I go back to when I was showing the formulation here, that I believe is this. So actually the way I was framing this problem is that you get the dimensionless input that yield the most predictive dimensionless output. So you can
okay.
both of them free if you want to. Or if you want to, you can fix the output. In that case, you solve the same optimization, but there is no pi naught. That is the one that you like. And sometimes that might be preferable because maybe you have a dimensionless output that you like for whatever reason. So in that case, you only optimize the input. But sometimes it's better to optimize both at the same time because then if you don't mind, whatever, you don't have any preference about what should be the dimensionless form of your output, because in that case, you guarantee that you will get the best answer. And in some cases, actually, it doesn't matter. Like that whatever you choose to let the output free or not, then you will still get the best possible answer. So it's a bit problem dependent. Yeah.
Yeah, thank you very much. Really a very excellent work and very good talk, because we have one project in the similar line, and I think this will help us a lot in our project. So thank you very much, sir.
Another question.
Thank you so much, Adrian. Do we have any other questions?
Yep. Hi, my name is Vivek and I'm a PhD student working with Professor Gagne. I also have a question about the last slides you were showing about the home isotropic turbulence case. Right. You can go to, let's say, the 71st slide where they're aligning. Yeah. So I understand this, but I have a question. How important have you tried reconstructing the high fidelity solution at t equal to 10 timescales from the LES simulations? And how important do you think that problem is? Is it a valid problem in your opinion?
So that's a very nice question, actually, that I didn't show here because, again, I thought that was a bit, maybe could be confusing, but you actually can do the other way around. Instead of filtering the solution at the DNS and comparing that with LES, I could do the opposite. I could invert the filter in the LES and compare with the DNS. And in that case, you also get the right answer. And the reason goes back to this. Information is conserved. It means that you have everything you need to recover the original flow field. So the answer to your first question is yes, you can do it the other way around and you will recover exactly also the small scales. Now, about the second question, my answer would be it depends. How useful is to recover the small scales? It depends. For this reason, in most of the problems that I care about, it's not only that it's not relevant, it's like it's impractical. So the whole point for me doing LES is that I cannot even fit in memory the small scales. So imagine that getting my small scales imply getting 10 to the 30 numbers. I mean, first, that's uncomputable, and there's no computer that can have that in the memory. So from my point of view, there is no merit in recovering the small scales. But I think that that's because of the problems I care about. Maybe there are other problems. I can imagine, for example, measuring experimentally, and maybe you want to reconstruct the small scales. And then in that case, there is value on that because you want to recover that. Again, in my case, I don't try to do that because I am assuming that that's impossible. It defeats the purpose of creating the reduced order model to begin with. But in other setups, then yes, you just need to make sure that it's possible to actually obtain the small scales in the problem you care about. This is kind of a low Reynolds number problem. Yeah.
Yes, thank you for the answer. I have just a follow-up question. So when you said you will invert this differential filter and reconstruct the small scales, did you mean it will align with the DNS solution like phase-wise or in a statistical sense?
No, point-wise.
Point-wise. Okay, all right.
Yeah, exactly.
Thank you. Thanks for a nice talk, and thank you for answering my questions. Thank you.
Thank you so much, Adrian, for your time. It was a really nice presentation, and I think that now it's time to move for our second speaker. I think that David is here. So once again, thank you so much, Adrian. David, could you please see your screen? Okay, our second speaker today is Professor David John, DJ Gagne. He's the head of the MILES Machine Integration and Learning for Earth System Group at NSF National Center for Atmospheric Research. His research focuses on developing and using advanced machine learning methods for emulation, uncertainty quantification, and physical understanding of atmospheric phenomena across the space and time scales. He has also conducted extensive research into the elements of trustworthy AI. David John began his conducting machine learning research as an undergraduate intern in 2007 and received his PhD in meteorology from the University of Oklahoma in 2016. He has worked at NSF NCAR since then, first as an advanced study program postdoctoral fellow and then as a machine learning scientist. He serves as a co-chair of the WMO AI for No Ghosting pilot project and on the WMO WWRP Now Casting and Mesoscale Research Working Group. David, thank you so much for your time today. And with this short introduction, you can start whenever you're ready.
Thank you, Juan. Excited to be here. Thank you for the invitation to speak. So I'm David John Gagne. I'm going to talk today about our project we conducted at NCAR about it was a very accelerated one-year project to localize simulated methane leaks and large eddy simulations with transformer machine learning models. Want to give a shout out to the team that worked on the project, especially Jeremy Sauer, who I saw was in the audience today, as well as Charlie Becker, Domingo Munoz Esparza, Thomas Martin, and Brian Travis. So the motivation for this project is that when natural gas drilling and production and extraction is going on, there's a lot of equipment involved in kind of getting it out of the ground and processing it and storing it before it goes off through the pipelines to wherever it goes to be used. And throughout that whole process, there's a lot of opportunities for leaks, and leaks can be sometimes quite large. And because like methane, natural gas is invisible, you can only really see it. In this case, it's like an infrared camera. And so the leaks basically they have like local hazards. Like if you just have a lot of methane leaking out, it's bad for like air pollution. It can also ignite and cause explosions. And there's also just like you're leaking a bunch of gas that could be sold. So it's there's economic aspects of it too. Methane is also just a very potent greenhouse gas. So if we can minimize leakage, that would minimize kind of the amount of methane going straight into the atmosphere. There's been a lot of research into how to improve methane leak detection at different scales. So they're at like kind of larger scales. There are satellites now that can detect methane leaks. That kind of hey, this coming from this like particular drilling site. But the satellites, they don't localize very well. You only get a pass so often if it's a polar orbiting satellite, for instance. So it doesn't give you the fine scale details that you can have if you actually have in situ observations. And for where we have in situ observations, often the systems are set up with point observations of methane concentration and wind, but getting high accuracy at localizing from point observations is really, really challenging because you get a lot of, there's like kind of broad scale atmospheric conditions, different turbulence regimes. The equipment itself causes the methane plume to circulate in different ways. So it can be hard to backtrack exactly where the methane is coming from. And a lot of methods kind of make a lot of assumptions to make them tractable, but those assumptions can cause a lot of false alarms. So with I think another problem we're running into as well is just there isn't a lot of data on methane leaks. You have to actually simulate a methane leak. You simulate it in a model where you release methane in the real world and then try to detect it and you know where the release is coming from. But that's all very labor intensive to do that. So kind of the premise of this project is, what if we build a machine, use first really high fidelity simulations of methane leaks to understand the turbulent dynamics and capture all of those details at extremely high space and time resolution, and then take a machine learning model and giving it only what kind of we would expect observation equipment to see. Can we invert the problem and detect where the methane is coming from and what the leak rate is? And we want to not just have just any arbitrary machine learning model. We want one that can generalize across not just one equipment setup, but lots of different equipment setups. So you could apply it potentially at lots of different drilling sites, of which there are thousands more. There's a lot of them throughout the world now. So that how do we first of all get you oriented on like what do these drilling sites look like? So this is an example of a site. You have wellheads. So this is basically where the like if you drill basically you drill holes in the ground to get into the pockets of methane, and then usually if you're doing fracking, you inject like water with lots of chemicals in it, and to kind of break up the rocks and release the methane from which is extracted. And so once you break up the rocks, you get the wellheads get the methane out. The methane is mixed with a bunch of other stuff, oil and other particles and whatnot. So you have these separators that basically separate the methane from everything else. And then we have storage tanks where you store the methane until it either is trucked out or if there's a pipeline that takes it out to a refinery or another facility. To detect the methane leaks, you usually have a set of sensors that are placed kind of around the area you want to detect, so that you can so you have some combination of anemometers to detect the wind speed and direction, and then CH4 sensors that detect the concentration of methane. And so given this setup, we want to basically, given these like just the information from these sensors and knowing where all the equipment is, we want to be able to say where like if there's a leak, which equipment piece is it coming from and how fast is it leaking? So what does the data look like? We want that as the wind varies in direction, like at very fine time scales, the plume itself will shift around, and so different sensors will record sometimes short spikes of high concentration of methane, and then it'll go away. Other sensors won't record anything or very small spikes, and so from these time series, the idea is if you can track how the wind is moving and how the time series is varying, then you should be able to kind of both knowing where methane is high and where it's low, you should be able to kind of invert and figure out which source is the likely culprit for the methane leak. So where this can get challenging is that there's this is an underdetermined problem, and we don't really have enough observations of this to train a machine learning model. There's not enough conditions, not enough like different permutations of this. But if you have a high fidelity simulation with really realistic turbulence, then we might be able to train a machine learning model on the simulated data, and vary it up quite a bit in whatever way we want. So it's seeing a variety of conditions, and then we can see if that will that generalize to the real world. This is a kind of a multi-phase project. So we started with like extremely idealized simulation. So we ran one large LES with multiple plumes being released at the same time, and then have some sensors downstream of the plume. Basically, it's a 2-meter resolution, a 50-meter kind of box, only one type of turbulence, limited wind direction, very few cases, just to get the algorithm working. And this allows us to figure out some of the like geometry and other issues we needed to pick out in order to train a robust model. And from this, we then moved on to phase 2, where we actually put in, so this had no equipment, this is just plume leaks. We took a particular site that's being used for validation called the METEC site, and put that equipment into the fast Eddy LAS, the 200-meter box at 0.5 meter grid spacing. And then we rotated to get some variety in infrastructure location, we rotated the infrastructure around in different configurations so that the model wouldn't just learn that, hey, this tank's always over here. We wanted to have the model learn the relative geometry of the sensors and the pieces. We also were able to, within each simulation, launch multiple like leaks, but kind of in parallel. So since they're sort of passive tracers, they're not interacting with each other, but that gives us more training data per set of atmospheric conditions. And then in phase 3, we wanted we trained our models and kind of off the phase 2 data, but then we wanted to apply them in kind of a more real world-ish situation with terrain and buildings and real world weather conditions. So we had WRF coupled to fast Eddy of multiple nests and using 20 different case days along the front range. So we also get mountain effects and different large scale forcing conditions. And then we can compare this with actual observations being taken at these sites at the same time to see if how well are we capturing the how close the simulation is matching to real life, and then if we run with real life data, how far do we still maintain our accuracy? So our output from fast Eddy, we have multi-scale large Eddy simulations. We have 1,000 distinct emission scenarios at half-meter resolution with 1 second output for over a 25-minute period. One type of infrastructure going to be rotated around, so we get different scenarios. And then you can see there's different plumes go off in different directions. We use different turbulence conditions, so weakly stable, neutral, and convective. So we capture the whole diurnal cycle. And then we also span different wind forcing, so high winds versus lighter winds. And then simulated also releasing from different pieces of equipment. We also moved our sensors themselves around too in these different simulations. And we could basically move the sensors around by just picking different grid cells and vertical levels to pull from for our as pseudo sensors. And as far as this is the first simulated emissions database of its kind in the world. So and it was a very large amount of effort to put together. We used over 200,000 GPU hours of NCAR computing to date. Which is getting into kind of 1 year's worth of lab allocation at NCAR or basically a large allocation request to do this. The interim data volumes are on the order of petabytes, and so there's a lot that had to be done to process this into something that we could feed into the ML model. So then our data workflow, so we have, again, our emissions instances we can launch from different locations. Our coordinate framework, so we had to figure out geometry that would generalize and not just be something that we wanted to be able to make sure it's not just learning from one direction. So we have we use a wind relative coordinate framework where we look at the average wind direction or wind vector over our evaluation period or input period, and we use that to orient all of our in kind of a polar coordinate system where things are in terms of range and azimuth for our sensors and our potential leak locations. And then we kind of categorize at the equipment level. So we also we basically plug in representations of each of these pieces of equipment as just kind of its location in the system, and that knows that is a leak location based on how we put it into the model. And then with our sensors, we get time series from each sensor. One of the sensors will have an anemometer, so just wind information. The other sensors will just have methane concentrations, and we can we want to be able to basically have a model that can handle different numbers of sensors and different locations of sensors. So it's not just completely tied to one configuration. We initially tried a completely random setup for sensor locations, but found that was suboptimal because it would just miss a lot of plumes. So we basically did some variations in this kind of ring setup. as what we kind of settle on for our final configuration, which is kind of more realistic to how one would set these up at a given site and would give us the highest likelihood of capturing a plume no matter which direction it's going in. For the machine learning portion, we wanted to use a modeling framework that is very flexible in terms of how many like sensors you could put into it and be able to learn a lot of give it kind of a lot of relatively raw data, have it learn a lot of the internal representation that could be very accurate. And so we turned to the transformer, which is basically the machine learning architecture that powers pretty much all of the modern large language models and a whole lot of other applications in various forms. So this came out from a paper in 2017, Attention is All You Need. And the idea is you start with these what's called attention layers, which you take you feed in latent vectors and numbers for your queries, keys, and values. And often it is done as what's called self-attention. So you basically take the same vector of information, and then you have other neural network layers that are called linear layers that convert that into another value for each of these things. And then you calculate in this part of the block, you calculate attention weights that basically say between like different elements of your different vector representations or tokens. You calculate like the relative weighting between them, and then use that to multiply across your queries and keys with your weighted by your attention on your values, and then that goes forward into the model. Then you can do this with not just one calculation of the attention weights. You can do multiple versions of this, and then concatenate them together and send it through the model even further. And then if you stack a bunch of these together in a clever way, you start by like in language, you take it's like a sentence, and convert each word into a token, and the relative position of each word is added on to that representation with what's called position encoding. And then you do the self-attention. You can do it multiple times, transform your model, normalize it. And then if you have let's call it a target sequence, so basically like you're translating from one language to another, in your target sequence, you then cross attention with your initial source sequence and then make a prediction at the end. For the words, it's like the probability of in some large dictionary of words, what's the probability that this word is the next word in the sentence? And then in traditional language modeling, you go forward on that, and then you come back, add that word into the sequence, and then keep going, and then it learns to attend on itself and write out a sentence or a lot of sentences. And a lot of models are basically based off of this architecture. But since it's very flexible, you can give it varying numbers of tokens, and the model itself it trains a representation that can be flexible across lots of different combinations of things. We saw that it could be very useful for this kind of task where we don't have a fixed number of sensors or fixed sensor locations. So how we transfer into this task is we take our sensor time series, and to tokenize it, we take each sensor time series and break it up into sub blocks. So 30 time step, 30-second blocks, and then we learn a neural network layer that will convert that block of methane concentrations or normalized with a quantile transform or wind values and position information about like kind of that relative position encoding. We encode that into the tokens are these 30-second blocks for each sensor. And then the sinusoidal position encoding basically is for where that block is in time, and then the position is kind of attached onto it as well. Then we have the model kind of learn relations between the different sensors by passing it through these transformer encoder blocks. So we have 6 of them. Our latent vector is we have 384. We have multi-head attention of 24 heads. We tried a bunch of different configurations, and this is the one that seemed to work the best. And then after we do all the transformer encoding, we then pass this information to the transformer decoder, which are like kind of destination tokens, or like what we're trying to predict are, we give the relative locations of all the pieces of equipment. We cross that with all the sensor information, and we do that multiple times, and it kind of steadily refines the information to basically take information about where the methane is high and where it's low, so it can learn both, and then feeds that into a softmax that gives you a probability of that particular piece of equipment is the leak source, and we essentially apply the same weights in parallel to each potential leak location, which kind of gives the model a lot of opportunities to update and handle like kind of all this cross information. With those probabilities, we use that to actually weight the average of these different latent representations of each potential leak location. We weigh that together into one latent vector that we then feed into another dense layer that then gives us the leak rate. And then we jointly optimize all of this with a binary cross entropy loss or a mean absolute error loss. Train for 75 epochs, batch size of 128, play with the learning rate for those who care about that. Pretty standard neural network training at that point. So that's kind of the overall model. So then the question is, how well does this actually do in practice? So for our skill assessment overview, we have, again, we're looking at the METEC site. We have different pieces of equipment that are numbered. And then we have our sensors. Ideally, our main assessment criteria is top accuracy. So we have top 1, 2, 3. So top 1 accuracy means you have to get, like, we rank the sensors by probability, or like the potential leak locations by probability of leak. And then like top 1 accuracy is to be correct, you have to, the most likely sensor has to, or most likely leak location has to be the correct one. Top 2, with like either of the top 2 have to be correct. Top 3, so top 3 is a little bit more generous, and top 1 is very strict. You can keep going out to further top X. It kind of levels off eventually. The idea, like from a real world perspective, is like how many sensors, how many places does the like the technician have to go look at with his IR camera to actually find the right leak. So ideally, you want to get like minimize that distance as much as possible that they have to go search around. So we compare this across different semi-idealized conditions. So one is weakly stable conditions, which is you see in mid to late evening hours or pre-dawn hours. Low levels of turbulent kinetic energy, weak near surface winds, and so you get the plumes are fairly steady, but they do meander back and forth to some extent. In this scenario, the effects of the infrastructure on the plume are most significant. So because of the meandering, it's going to wrap around like the tanks, and then that can shift the direction of the plume. So that can make it a bit more challenging. We have near neutral conditions, sort of kind of the in-between. This is usually you find in the early evening or early morning around sunrise and sunset. You get more shear turbulence production, and you get some more variability in plume direction. The plume itself is, you get some more higher concentrations that fill up. There's also more spatial and temporal variability in the plume, and you still get infrastructure impacts. So it's moderately challenging. And the final is convective, where you can get a lot of variance in plume direction, but the effect of the equipment is relatively minimal. So basically, like if your sensor detects the plume and you're kind of following the general wind patterns, you should be able to backtrack it. But you're also just getting a lot of turbulence and mixing from both from higher altitudes too. So in terms of our idealized performance on held out simulation, or like held out examples from those that we compare with those that we trained on, but sort of still in this idealized world, we end up finding configurations that were extremely accurate with kind of in the top 3 accuracy, we were getting in kind of for most of the sensors, we were getting kind of in the like 80 to 90% accuracy range. For top 1 accuracy, it was, like, varied a lot between sensors, but or between pieces of equipment. Like, it range anywhere from like 40 to 50 to like that 80 to 90%, depending on the exact piece of equipment. In terms of equipment group, we had accuracy in the high 90s, so we could at least localize to a particular block of equipment. So basically, this gives us some pretty good confidence that at least with this data set, we were learning the right things for the right reasons. Earlier on in the project, we definitely had some instances where we didn't seem to be learning the right things for the right reasons, and so the generalization was fairly poor. But with like a lot of tweaking of the architecture and giving it enough data, that all seemed to combine to give us a good result. And this took like all emission scenarios and a lot of sensor layouts. In terms of leak rate, we like for the most part we were getting fairly close within like kind of 1 or so of the leak rate values. There at lower leak rate values, we seem to get more variance in the outcome, and we're often a little bit more incorrect. But at higher leak rates, we seem to generally get better results. So that was kind of good to see, and also making sure we were simulating across a wide range of leak rates turned out to be very important to get good performance. And we're also able to do all this with one combined model, and we had to do some tweaking around to get the right combination of things. Also, so that the model would learn to localize in conjunction with predicting the leak rate. So it definitely took some effort to get all that to work well. So works great in kind of the idealized simulations. What happens when we go to real world observations? Well, the bad news is performance drops a lot. So our top 3 accuracy drops from like the 90s to 15%. Some of this, and we compare a couple of different field campaigns. Some of this appeared to be just we had some somewhat different setups where the TDLAS, I believe, are the methane sensors. And this each one was collocated with an anemometer, which is a bit different from the one anemometer setup we had trained on. And so that can have an effect on generalization. We also had like a different set that had different kind of 8 sensors. Only some of them were collocated anemometers, and only had 2D wind observations, whereas we trained with 3D wind data, and the W definitely had an impact on the results. But we were able to look at like it didn't fail in all cases. There were some where it did fairly well, and in this case, it was one where we had quite strong winds. So this is like a fast-day simulation of a particular case that was forced by I think the wharf conditions. Basically, kind of fairly narrow plume, not a lot of a variance in the direction. So it should be a relatively easy thing to localize. In fact, we generally did a pretty good job getting the right sensor. However, we go to like a case where we did poorly, and in this one we have basically a lot of variation in the plume. We have sudden shifts in wind direction, a lot of other like kind of these small vortices kind of propagating through the equipment region, wind direction changing quite suddenly, and kind of going from one sensor to another. And so the model basically never really picked up on the correct leak location, except maybe for like 1 or 2 time steps, and for the most part was picking out other pieces of equipment and varying a lot between them. So kind of in some ways this is like sort of its own form of uncertainty quantification. If you're not getting a consistent prediction between time series, it's a situation where there just isn't good. The model has fairly low confidence. And you can see kind of like this is the actual one, and then for the most part, our predictions were well off. Some bit of good news though with our let's say workforce fast eddy simulations, we have our accuracy, like while still not nearly as good as our um, original like kind of fully idealized data, we're still getting some decent accuracy at the group level and okay accuracy, but not great at the individual equipment level. So they did seem to generalize to some extent as long as you're still in simulated space and not dealing with kind of real world observations that tend to be a lot noisier. We've seen this on some other problems too, where like we're trying idealized data and really sucks at real world data. And one of the things we've worked on with that in another project was actually adding style transforming realistic noise into the as part of the data processing pipeline. So that may be something that we could do as a follow-on. If we end up doing a follow-on to this, that could be a direction we could go. There's also other ML optimization algorithms and models that can handle like noisier targets. So that may be something we look into, or try with different simulations. Or there's I think a lot of opportunities there to see if we could generalize things further. But kind of in summary, we like having this really high fidelity LES output that can capture the turbulence and dynamic structure affecting the evolution of the methane plumes. I think it provides an opportunity as a really compelling data set and problem to test the limits of what machine learning can do to localize methane leaks. We were able to put together a transform model that in under idealized settings could perform really accurately, but still had generalization issues as you brought it into more real world conditions. So the code for this is open source. We're still in the process of working on a paper for this. But if there's interest in collaborations or using the data, like talk to Jeremy, who's also on the call, and we can potentially work on like look at follow-on opportunities or are there any other points of interest. So with that, happy to take some questions.
Thank you so much, David. That was a really nice talk. Do we have any questions from the audience?
I have one question.
Please, Hassan.
This is Hassan from Brown. So I see when you go to the realistic case, you actually have that drop in the accuracy. Can you can you pinpoint what causes this actually when you go to the real case? Is it just the actual data that you're working with, the uncertainty in the data? What is the main reason for that? If you can make a comment on that, it's the first question that I have here.
Yeah, I'd say we didn't completely, like, I think, nail down all the sources of the drops in accuracy, or I think leading hypotheses. One, for some of these cases, we're seeing basically it's a very challenging, like in the example that I showed with let's see, our kind of poor case. There's a lot of changes in wind direction, relatively low wind speed, a lot of equipment effects, a lot of vortices, things that make the assumption like being able to sort of backtrack the plume flow harder to do consistently, and just not getting like the kind of spikes in concentration were relatively small. So I think all of those combine for drops in performance. In some cases, there's some missing data. So there's like a gap right here, for instance. I don't know, Jeremy, if you have any other thoughts on the drop in accuracy. I think that there was also some issues with like data quality for some of the real world observations where we couldn't completely source like exactly how they were calculating some of the concentrations and position information. Yeah, Jeremy.
Yeah, I would say our main findings were that there were two sources to the fall off in accuracy. One was the difference between real world uh, plume transport conditions, as exampled here in the animation. In a real world case, nothing is actually stationary, right? Everything is always completely dynamic and has a massive spectrum of scales involved. In particular, those cases where there were weak and variable winds is where the algorithm was most challenged to find a consistent upstream wind direction and an upstream location. After we started training on our multi-scale hindcast cases and we were exposing the algorithm to instances of that kind of flow field, these very dynamic flow fields, the accuracy improved significantly. And in fact, we could show that when we were inverting the virtual emissions from our hindcast simulations, the accuracy of the model did get much, much higher. When we look at raw observations from the field, the second source of what we think was the massive fall off in accuracy was the real circumstance that real observations have problems. They're not perfect. When we extract the time series from the model, there is no noise, there's no lack of calibration of instruments and aspects like this. When we had actual observations to compare against that led to those very, very low numbers in accuracy, we actually had no control over those observations. That data was simply shared with us, and we had to apply it the way it was. We think that there were quite a few data quality control issues that also contributed to the drop off in accuracy.
Yeah, I understand. And so the wind field that you use here is it the simulated wind field, correct?
That's correct.
But the methane concentration is actually coming from the data, the sensor reading.
Well, no, sorry. During the training periods, all training data is virtual and simulated. So both the flow field information as well as the plume transport, that is all simulated. In the model inversion, in the inference mode, you can then apply it to extracted time series either from the model or just raw observations, being a combination of, again, some sonic anemometer time series as well as methane concentrations. But all training is on virtual data.
Okay, I see. So when you go to the inference for the real case, how can you make sure that the wind field that you have is consistent with the sensor reading of the methane?
Well, because it's not a full wind field. It's simply a time series from a single location where a sonic anemometer is placed, right? So we don't reconstruct the full wind field in the inference mode. The inputs to the machine learning algorithm are strictly point-wise measurements of methane and a single sonic anemometer that gives you the velocity at a given point.
Okay, I see. I mean, I have some more questions, but I want to also give floor to other people if they have questions.
Do we have any other questions from the audience?
One quick question. You said that the data is accessible if we want to look into it and like if we want to like play with the data a little. Is it something that is accessible?
The training data is not in a public repository per se, but we could certainly talk about making it available to parties interested in using it through a file transfer. It'll be a really big file transfer, though. I mean,
yeah.
Yeah.
And the field that you consider in these examples, from the figures that you were showing in the presentation, it seems that it is like around a 200 by 200 meter field. Is that correct? Just wanted to confirm that I understood it correctly.
So that 200 by 200 meter domain right there, yeah, that's actually an extracted portion of the full domain of the LES simulation, right? Because there are, the boundaries are actually much further away from this area of interest, which is 200 meter by 200 meter. The training data we use, though, is all extracted time series from that 200 meter by 200 meter block.
Okay, I see. All right, great. Thank you very much.
The training data is three-dimensional, right? Fully 3D?
No, so we like take the 3D block, and then the model only sees the time series from these individual sensors. So it doesn't see all of the complexity of the we're showing this as an example of what's, so you have a sense of what's going on, but all the model sees is go back to this one, is basically just methane concentrations and at these diamond points, and then at this diamond plus X, it sees the wind speed in UVW, and it's just the time series.
Got it. Thank you.
For the neural net, we chop this up into 30-second blocks, and that's what goes through the model, and that's how the attention and transformer pieces are applied to it.
Thank you very much. How about the simulations? Are they 3D?
Yes.
Do you have any insights about what if somebody had prepared that training data? I mean, the simulations in 2D, would that, I assume you would lose some accuracy, but have you done that experiment by any chance, evaluating or have any insights on that? What if somebody had prepared all these simulations in 2D and then would use that to train the model?
Yeah, Jeremy, do you have any comments on that?
Yeah, I mean, I guess I would say, right, like fundamentally, by definition, atmospheric boundary layer turbulence is three-dimensional, and therefore transport of plumes is three-dimensional. You could perhaps look at strictly two-dimensional information and thereby reduce the complexity of the space you're trying to solve the inversion problem in, I suppose. We did not, well, I'll say, we did not restrict ourselves to strictly sort of the two horizontal dimension components of the velocity field, for example. We always did include the vertical velocity component as well, although we did not find that it was a dominating feature in terms of importance in the inversion itself. I think you probably could look at something like that, although I think, especially when you talk about upstream oil and gas facility infrastructure, wellheads, for example, are maybe 1 meter tall. Tanks are 3.5 meters tall. So I feel like the problem is to some degree inherently three-dimensional, and a two-dimensional approach may be an oversimplification potentially.
Thank you.
I did want to just mention, yeah, the LES simulations and the entirety of training data were always extractions of time series information from different points in an LES simulation. And as DJ mentioned, a given simulation, we could place and extract an arbitrary sensor configuration, right, of time series, right? So we would take a given simulation and say, for example, sample 36 different sensor configurations where the sensors were located at different places, and maybe the sonic anemometer came from a different place within the three-dimensional LES space. I mean, the full training data set in terms of the LES simulations is quite dense and quite expansive. And what we sampled from there was really what was used in the training of the inversion model.
I have another question about the simulations, like the one that its animation is showing. So are these, for instance, representative winds of that area that you did the experiments? For instance, you found a week that week is, let's say, representative of the situation in the field, and then you forced that with boundary conditions and ran something like WRF, or could you please elaborate on that?
Yeah, that's just about exactly correct, right? So this particular simulation is a case day from March 12th, 2023. During a certain period of time, the leak is emitted from the corresponding experimental leak during this experimental campaign. So these simulated conditions are a hindcast, and they're a multi-scale hindcast. So first we run WRF at mesoscale resolution of 3 kilometer. And then we nest within that WRF simulation that runs from essentially her reanalysis. We nest within that a very, very fine scale, actually 2 nested fine scale LES simulations, a first hop from 3 kilometers down to 5 meter resolution, so that we kick up the actual statistically accurate turbulence conditions within that very, very near surface layer at 5 meter resolution. And then we do one more nest on this very limited extent area at 0.5 meter resolution, 50 centimeter resolution, where that's nested within the 5 meter simulation itself. So we do this, what we call multi-scale hindcast, in order to try and replicate the conditions experienced on that day during that particular emission case.
That's impressive, going from 3 kilometers to 0.5 meter. Given that you also had wind sensors there, did you have a chance to compare your simulation with observations and assess the scale of your high-res wind?
Indeed, we do, and that is, that's all material that's going into the publication we're working on about the accuracy we found in the hindcast simulations with respect to winds and not only winds, but then downstream methane concentrations. Some cases did very, very well. Challenging cases were typically the weak and variable wind cases, where obviously in a given moment, a given gust of wind may not have exactly matched the observation. And what we have to do there in terms of assessment is basically settle for the notion that we are statistically correct throughout the simulated period, that the magnitude and essentially the spectrum of turbulence observed is statistically representative of the day, right? We're never going to match every single eddy, but statistically, if we match the turbulence forcing conditions and generally the wind direction from moment to moment, then we feel like it's a pretty decent representation of the actual case day.
Thank you very much. Very nice work.
Thank you.
Thank you so much, David and Jeremy. Do we have any other questions from the audience? It looks like we do not, so I think that we can close the seminar for today. Thank you everyone for your attendance. Thank you so much again, David and Jeremy, for your nice presentation. And I hope you all have a good weekend.
Thanks. Thank you, Juan.
Thank you.